This Zoom session is being brought to you by the Fractal Bullseye Bubble Fire. For today, we go through 6.3 and 6.4, solving 6.3 is a matrix inverses and solving linear systems by matrix inverses. And 6.4 is, I think, a really convenient one about solving linear systems by determinants. All right, a matrix inverses. Well, starting from last time, I mentioned the identity matrix, I sub n, the n by n identity matrix, n by n, n rows, n columns, ones down the diagonal, zeros everywhere else. If A is an n by n matrix, then A times I sub n equals A, and I sub n A equals A. So I sub n is like the number one, like multiplying by the number one for n by n matrices. So, okay, so it's the equivalent of one in some sense. Now, just as there's the equivalent of the number one, multiplying by one for n by n matrices, there's also the equivalent of dividing by one by a matrix. So it's the reciprocal of matrix. It's called A inverse, written A minus one. If A is n by n, then A to the minus one is an n by n matrix, such as A inverse times A inverse A equals I sub n. So it's the equivalent of a reciprocal. And okay, sometimes it exists and sometimes it doesn't. Just like with numbers, you can't divide by zero. Well, there are matrices you can't take the inverse of. For example, 7, 4, 3, 2 times 1, negative 2, minus 3 halves, 7 halves. Upper left entry is upper row times left entry. 7 times 1 is 7, 4 times negative 3 halves that's not 3, that should be a 6. Oh, my apologies, I'm gonna have to change 7. This is page 1. 7 minus 6. This should be a 7 minus 6. Upper right is upper row times right. 7 times minus 2 is minus 14. 4 times 7 halves is 14. Negative 14 times 14 is 0. Lower left is lower row times left column. 3 times 1 is 3. 2 times minus 3 halves is minus 3. 3 minus 3 is 0. And lower right is 3, 2. Lower row times right column. 3 times negative 2 is negative 6. 2 times 7 halves is 7. Negative 6 plus 7 is 1. I'm going to have to change this in the canvas. And if we multiply them the other way around, let's see. 1, negative 2, negative 3 halves, 7 halves times 7, 4, 3, 2. Upper entry is 1 times 7 minus 2 times, plus negative 2 times 3, 7 minus 6, which is a 1. Upper right entry is upper row times right column. 1 times 4 is 4. Negative 2 times 2 is minus 4. 4 minus 4 is 0. Lower left entry, lower row times left column. Minus 3 halves times 7 is minus 21 over 2. 7 halves times 3 is plus 21 over 2. These add to 0. And lower right entry is lower row times right column. Minus 3 halves times 4 is a minus 6. 7 halves times 2 is 7. Negative 6 plus 7 is a 1. So either way, when you multiply either way, you get the 2 by 2 identity. So the inverse of 7, 4, 3, 2 is 1, negative 2, negative 3 halves, 7 halves. In general, the inverse of a 2 by 2 matrix A, B, C, D is 1 over AD minus BC times D minus B minus CA. I like to think if we flip through this diagonal, so A and D change places and B and C flip signs, then we have this thing AD minus BC, 1 over that. If this is 0, then the inverse is not defined. So, all right. For example, if we try the inverse of 6, negative 3, 8, 4, well, we flip the 4 and the 6, 4 and 6. We flip the signs of 3 and 8, 3 and 8. And this thing here, called the determinant, we'll see it in the next section. 6 times 4 minus negative 3 times negative 8, which comes up to 0. And since we're dividing by 0, the inverse is undefined. But now let's try 0.4 minus 1.2, 0.3, 0.6 inverse. Well, okay. We flip these two positions, 0.6 and 0.4. We flip the signs of these two, 1.2, negative 0.3, and we multiply by the reciprocal of 0.4 times 0.6 minus 0.3 times minus 1.2, which when you work it out is 1 over 0.6. So we take this matrix and divide each of these by 0.6, because that's how you multiply a matrix by a number. You multiply each entry, and this comes out to 1, 2 minus a half, 2/3. And I'll leave it to you to check that this times this is the identity. Now, the point of a matrix inverse is that you can do the equivalent of transposing. If you have a ordinary system, AX equals B, you divide both sides by A and get X equals B over A. Well, similar with this. If A is an n by n matrix and X is an n by 1 column vector, basically it's a vector full of variables, equals B, an n by 1 vector full of numbers. AX equals B, then you multiply on the left both sides by A inverse. A inverse A is its identity. In times X will just be X. So X equals A inverse B. For example, let's solve this system. Negative 3x minus 5y equals 4, 2x plus 3y equals 0. We can turn these two into a matrix negative 3, negative 5, 2, 3 times the column vector xy. Minus 3x minus 5y here, 2x plus 3y here. And then here, we put the column vector 4, 0. So AX equals B. So we multiply both sides by the inverse of negative 3, negative 5, 2, 3. Get xy equals negative 3, negative 5, 2, 3 inverse times 4, 0. All right, so to solve this, we flip the positions here, 3 and negative 3. We'll flip the signs here, 5 and negative 2, times 1 over negative 3 times 3 is 9 minus 2 times negative 5, that's plus a 10. Okay, 1 over negative 9 plus 10 is 1 over 1, which just goes away. So we're left with 3, 5, negative 2, 3 times 4, 0, and here we go. 3 times 4 is 12, 5 times 0 is 0, so 12 plus 0 is 12. Negative 2, negative 3 times 4, 0 is 2 times 4 is negative 8, plus 3 times negative 3 times 0 is 0, negative 8. So xy equals 12, negative 8. X is 12, y is negative 8, and we've solved the system. Here, 2x plus 5y equals 2, negative 5x minus 13y equals 20. So 2, 5, negative 5, 13, that's the coefficient matrix, times the column, the variable column vector xy equals the column vector 220. All right, so we multiply on the left by the inverse. So xy equals 2, 5, negative 5, 13 inverse times 220. All right, to find the inverse of this matrix, we exchange the 12 and negative 13, 2 and the negative 13 here. We flip signs here, negative 5 and 5. And we take 1 over. 2 times negative 13 is negative 26 minus negative 5 times 5, that's plus 25. Okay, that's 1 over negative 1, which is negative 1, which multiplies throughout by flipping signs. 13, 5, negative 5, 2. That matrix times 220. Here you go. 13 times 12 is 26, plus 5 times 20 is 100. 26 plus 100 is 126. Lower entry, lower row times the column vector. Negative 5 times 2 is negative 10. Minus 2 times 20 is minus 40. Minus 10 minus 40 is minus 50. So xy equals 126, negative 50. So x is 126, y is negative 50. Here we're solving for a whole matrix. Though in my opinion, what basically is we're solving 3 linear systems. 3, negative 2, negative 4, 3 xu equals 1, 2. 3, negative 2, negative 4, 3 times yv equals 0, 1. 3, negative 2, negative 4, 3 times zw equals negative 1, 3. No big difference. What we do is we multiply on the left by the inverse of this matrix. So after canceling, we get x, y, z, u, v, w equals 3, negative 2, negative 4, 3 inverse times 1, 0, negative 1, 2, 0, 3. All right. So to find the inverse here, we flip these two signs, bing, bing, there they are. Stay the same really. And change the signs here, positive 2, positive 4. And that times 1 over 3 times 3 is 9 minus negative 4 times negative 2 is 8. 1 over 9 times 8 is 1 over 1, which is just a 1. Then 3, 2, 4, 3 by the usual matrix multiplication gets you 7, 2, 3, 14, 3, 5. So this matrix equals this one. Now that's for 2 by 2 matrices. Higher matrices, it's a little more trouble. And in a certain sense, it's diminishing returns because basically what you do is use row operations to find the inverse. But you use row operations to solve linear systems anyhow. So it's just sort of the same thing again. Here's what you do. You have an n by n matrix where you do find its inverse by row operations. You start out by writing the matrix n by n matrix A next to the n by n identity, I sub n. Write them next to each other to get an n by 2n matrix. And you use row operations to turn A into the identity matrix. And those same row operations will at the same time turn the identity into the inverse. So when row operations turn A into the identity, then they turn those same operations turn the identity into A inverse. For example, -3, 2, 3, 0, -1, 3, 1, 0, -2 inverse is what? So we write that matrix here, -3, 2, 3, 0, -1, 3, 1, 0, -2. Write it next to the 3 by 3 in identity, 1, 0, 0, 1, 0, 0, 1. And I'm going to do a series of row operations to turn this into the identity, 1, 0, 0, 1, 0, 0, 1. All right, so let's see. I'm going to pivot on this entry here, use it to cancel out this 3, this -3. So add 3 of row 3 to row 1. -3 plus 3 times 1 is 0, 2 plus 3 times 0 is 2, 3 plus 3 times -2 is -3, 1 plus 3 times 0 is 1, 0 plus 3 times 0 is 0, 0 plus 3 times 1 is 3. Okay, next I'm going to flip the sign of this row, so rescale it by -1, to turn this -1 into a positive 1. Let's get 0, 1, -3, 0, 0, 0, -1, 0. And meanwhile, I'll use this to cancel out this. So we'll add twice of row 2 to row 1. So 0 plus twice 0 is a 0. We put that there. 2 plus twice -1 is a 0. Put that there. -3 plus twice 3 is a 3. We put that there. 1 plus twice 0 is a 1. 0 plus twice 1 is a 2. 3 plus twice 0 is a 3. So far, so good. Oh, well, look, 0, 0, 3, 1, 2, 3. Well, let's divide this row throughout by a 3. Okay, that row becomes 0, 0, 1, 1/3, 2/3, 1. We're nearly done. Nearly. We have this row column is cleared, this column is cleared. We'll clear this column by pivoting on this entry. We use this 1 to cancel that. Add 3 of row 1 to row 2. We use that 1 to cancel that -2. So add twice row 1 to row 3. And long story short, you get 001, 010, 100, and this becomes 1/3, 2/3, 1. Same here. 113 here. 2/3, 4/3, 3 here. This is not quite the identity matrix. We need to flip to exchange the first and the third row to get 100, 100, 1. Doing that here, you get this here. 2/3, 4/3, 3, 113, 1/3, 2/3, 1. So this here is the inverse of this. The inverse of -3, 2, 3, 0, -1, 3, and 1, 0, -2 is 2/3, 4/3, 3, 113, 1/3, 2/3, 1. This and this are inverses. The graphing calculator, calculators such as this, say, has a matrix menu in which you can enter matrices and add, subtract, multiply them, and also find their inverses. Very convenient. Certainly it avoids all the troubles here. I'm not against you using a technology, so this is just that I want you to know how the mathematical principles behind the technology works. Of course, if I mentioned manual, you should always save your calculators manual. People have a bad habit of they buy the commodity and they throw out the instructions. That's a terrible idea. Keep it at hand. You'll never know when you need to know when you need to know how it actually works. All right. All right. Here we have a 4x4 matrix. 1, 1, 0, 3, -3, 1, 1, 1, 0, -2, 0, 1, 2, -1, 1, 2, 3, 0, 2. Its inverse, if you enter and hit the inverse, is this thing here. Minus 2/3, 1/3 is -2/3, 2/3, 221, -4 over 21, 8 over 21, 1 over 21, minus a third, minus a third, minus a third, 1/3, minus 11 over 21, 1 over 21, -2 over 21, 5 over 21. Okay. Uh, Calculating this by hand, well, it's doable, but as you can see, it's a lot of entries and with some nasty fractions. So save yourself the trouble. Now, the point is this. If we have this inverse is this, then you can solve this linear system because these are the coefficient matrix of that is this 1, 1, 0, negative 3, 1, 0, minus 2, 0, 0, 2, minus 1, 1, like here, 2, 3, 0, negative 2, like here. And so, okay, change it into a matrix problem times the inverse, then x, y, z, w equals this matrix inverse times 0, 8, 5, 13. And using this and multiply by this, yada, 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 we get x, y, z, w equals 8, 1, 0, 3. There you go. X is 8, y is 1, z is 0, and w is 3. And actually, if you jump to the calculator, then you might as well just, enter this as a matrix, enter this as a matrix, then write down matrix inverse A, inverse B, and push the button, and this comes straight out. So, all right, that's how we can use matrix inverse to solve linear systems. It's not that bad, especially at least for 2 by 2, because the matrix there, we have a closed formula for it, and that's actually not that difficult. There are closed formulas for higher order matrices, but it's a major pain in the neck. So, all right, let's see. Stop. Let's